All right, so it's time to go ahead and get started. My name is Suzanne Shantz. I want to welcome you to this session. This is a mini symposium on mesh adaptation techniques for numerical simulation, and this is the second part out of 3. We just finished with one session this morning. This is our second session, and then tomorrow morning we'll have another session. Sorry, I shouldn't say morning. I'm in the United States, so it's morning here, but it might be in the afternoon if you're in Europe, or maybe even in the evening if you're in Asia. But again, welcome for joining this session. This is co-organized by myself, along with Perloff Person, as well as Franck Ledoux and Adrienne Lassay. All right, and in this session, we're going to have 4 speakers. You should be able to see my slide that I'm sharing. The first speaker is, I'm not sure if I'm pronouncing the name right, but Capucine Legentile. Co-authors, you can see listed there. The title of this talk is Testing Scenarios, Geological Models, Local Interface Insertion in a 2D Mesh, and its impact on seismic wave simulation.
Hello everyone, I am Capucine Legentile, a second-year PhD student in the Ring team at Université de Lorraine in France. I will present you the results of my first year work about the local modifications of mesh geomodels and evaluation of these modification impacts. A geomodel is a model of the subsurface. It holds the geological structures of the field in study, including interfaces between units or materials, and faults. Because available data for computing such a model are sparse or have a limited resolution, the position of the geological structures are uncertain. For example, if the model represents a gas reservoir, it is difficult to check the model accuracy, and in particular, the accuracy of the position of the interface between gas and water. I will present you a proof of concept of my work with a seismic application on this synthetic model of a gas reservoir. A reservoir is a rock body that has sufficient porosity and permeability to store and transmit fluids. In a gas reservoir, the contact between gas and water is horizontal at the equilibrium. Each layer has different rock properties and different shear wave velocities. We propose to locally modify the initial multimaterial mesh domain by inserting the gas-water contact at 20 different depths between these 2 depths. After the interface insertion, the gas zone is above the water zone, and it is represented in gray in this image. After that, we want to know if the interface modifications impact the seismic simulation. To do that, we propose a practical approach to automatically update triangular meshes for physical simulations, and an assessment of the detectability of fluid contacts changes in reservoirs. To do that, we need an initial mesh and an implicit definition of the line that represents the gas-water contact. All vertices of the mesh have a value, and the chosen value describes the contact in the model. Thanks to that, the position of the line can be easily changed. The second step is the delimitation of the region that will be modified. Here is a reservoir layer. The third step is the level set discretization made by MMG. In the triangle intersected by the line, new points are created, but the triangle have a poor quality. The last step is the mesh improvement, also made by MMG, to have a good quality in the modified region. For each model, we run elastic wave propagation simulation, and the displacement is recorded. We first look at the seismogram at one receiver, shown as the green triangle in this image. Here, the depth error is 100 meters. It is the difference between the reference contact depth and the model contact depth. We can see that there is some differences here or here. And to compare the simulation results, I will show you in the next slide the quantification of the simulation difference. For each receiver located at the surface of the model, the L2 norm waveframe difference is computed. To more easily compare simulations, we choose a unique indicator, the mean of the error. There is the results, and we can observe a correlation between the mean error and the depth error. To conclude this presentation, we can say that the approach is validated in 2D, and we are confident for application of this approach to uncertainties on other geological interfaces, and for the extension to 3D. I present you a seismic application, but this approach can also be used in other physics, such as fluid dynamics. Thank you for your attention. I will be very pleased to answer your questions.
Okay, and with that, we're ready for our second video. The presentation will be given by Lorenzo Mingazzani. And the title of his presentation is Energy-Based Global Local Strategies with Adapted Mesh Refinement for the Phase Field Approach to Brittle Fracture.
Greetings everyone, my name is Lorenzo Mingazzi. I'm a PhD student from the University of Parma, and together with Professor Francesco Freddi we develop energy-based global local strategies with adaptive mesh refinement for the phase field approach to brittle fracture. The phase field approach to brittle fracture is a variational approach based on Griffith fracture theory for brittle material, where a scalar smooth field which represents the damaged state of the material is introduced, and cracks are represented as a transition zone between broken and unbroken areas of the material. Cracks nucleation and propagation are obtained via the minimization of an energetic function without the necessity of IDOC criteria. However, the minimization problem has to be solved over the whole domain, and a small cell size should be used in order to recover correctly the sharp crack topology. These two conditions, which are required to obtain accurate results, lead therefore to high computational costs. The main idea behind our work is to develop a refinement procedure which exploits two peculiarities of the phase field method. The first is the energy threshold which has to be exceeded in order to activate damage, and the second one is the width of the optimal damage profile process zone. So first, the active areas of the domain where damage occurs are determined by the usage of an energetic criterion, which is reported in the slide, therefore defining the active elements. Additional elements, which are the ones within the optimal damage process zone, are also included. The second step consists in the first H refinement process of both the active and the additional elements, and lastly, a second refinement process is performed only on the active elements. However, a distinction has to be made between the new active elements, which are the one determined at the current time step, and those are fully refined, and the old active elements, which were the one determined at the previous time step, which are refined only in the areas where damage exceed a set threshold alpha S. We developed two different refinement strategies, one global strategy and a global local refinement strategy. Here, the summary flowcharts for the two different strategies are reported. For the global strategy, we start by solving the global elasticity problem. Then we determine the active elements and their adjacent. Eventually, we perform the adaptive refinement, and lastly, we solve both the global displacement and damage problems on the refined mesh. For the global local approach, instead, we start by solving the global elasticity problem, from which we determine the active and the additional elements. We create the local mesh which undergoes the refinement procedure, and we solve the local displacement and damage problem. Using the information from the local damage profile, we perform the alpha adaptive refinement of the global mesh, on which we interpolate the local damage field. we investigate the effectiveness of our refinement procedure by studying two different numerical tests. The first one being a stable crack propagation test, also known as a surfing condition test, where a 2x1 rectangular domain is considered and the displacement is applied on the whole external boundary such that crack advances at a fixed amount at each time step. The second one, instead, is an abrupt crack test, where a 2x2 square domain is considered, which contains 3 pre-existing cracks. Here, vertical displacement is imposed on the top side, while block on the bottom side, and the horizontal displacement is imposed on the right side and blocked on the left side. So first, the results for the stable crack propagation test. It can be seen that are reported on the top left the global displacement damage minimization problem results obtained from the standard procedure. On the bottom left, the results for the global adaptive refinement strategy are reported, while on the right side, the global local refinement strategy results are shown. The videos reports the adaptive refinement evolution of the mesh for both the global and global local strategies, and can be seen how the obtained crack pattern and width of the damage transition zone coincide with the results obtained from the standard phase field solution. Next, the results for the abrupt crack propagation test are reported, and in the slide are shown the different meshes obtained at the end of the simulations. In particular, again, it can be seen how the different refinement strategies provide the same crack pattern obtained with the standard procedure, as well as the same optimal profile damage width. Some concluding remarks. Here are reported for the stable crack propagation test the diagrams of the effective fracture energy and the damage profile for the two developed strategy, which are compared with the standard procedure and the respective analytical solution, which both diagrams shows good accuracy. For the abrupt crack propagation test are reported instead the diagram for the fracture energy and the vertical force, both showing good agreement between the refinement strategies and the standard procedure. Moreover, below are reported the degree of freedom and the time required to run the complete simulation, showing an increase of performance ranging between the 85 and the 92%. That said, thank you for your attention.
All right, so our third speaker in this session is Parolov Person, and he'll be talking about implicit shock tracking for unsteady flows by the method of lines.
Hi, my name is Parolov Pearson at UC Berkeley. This is work together with my colleague Matthew Czar at the University of Notre Dame and my student Andrew Shee at UC Berkeley with me. It's about implicit shock tracking, and this is the extension to unsteady flows. If you get a chance, please first listen to Matt Czar's talk in this same session, because then I can speed over a little bit more the basic framework and the setting, and I can focus more on the unsteady flows. But I will give you a quick recap here. We use discontinuous Galerkin methods, which naturally allow for discontinuities between the elements, not within the elements. So if you don't move the mesh, it's unlikely that a DG method is good for handling shocks and discontinuities. But if you somehow magically manage to align the mesh with the discontinuities, the formulation itself is very natural for representing this without any need to refine excessively around the interface. We do this using an optimization framework and PD constrained, and we minimize an error type indicator to help move the mesh and align with the solution. So here's the steady framework where we actually have a mapping-based formulation, standard DG formulation where we multiply by test functions. We get two types of residuals. One is what I would call the square residual, namely the DG solution itself, with a certain mesh and a certain polynomial degree, and that we call little r here. And it depends on the solution and the mesh. So this is what you want to solve. It's just that we don't know what the mesh should be. But if you freeze the mesh X, this is exactly the DG, whatever DG solver you want. But we will also form an enriched residual for error indication. We could refine the mesh, but instead we bump up the polynomial degree. We call that capital R. And what we now do is that we have a minimization problem of minimizing basically this error, but we also add a little bit of mesh penalization for the mesh distortion. and subject to solving the PD correctly. So we will solve exactly whatever DG formulation you have, but we will use this optimization framework to move the mesh in such a way that this quantity is minimized. We will in general need mesh modifications, and we have worked a lot on curved mesh modifications like the collapse you see here. But in this work, our examples are a little simpler, so we will not focus on that here. This is a space-time solution, but let's just go straight to the method of lines, because Matt showed you these type of steady state and space-time solutions. So let's go straight to the unsteady case. In the unsteady case, we add a time derivative, and we discretized using ALE, arbitrary Lagrangian or Eulerian. One of the main differences is that the mesh velocity or the grid velocity shows up in the formulation, and we'll show on the next slide how we actually handle that. But basically, at the end of the day, the ODEs that we need to solve have a time-dependent solution term, and also the moving mesh, the derivative of the velocity of the mesh. We do exactly the same as before. We bump up the polynomial degree with capital letters. We now get an enriched residual, and it ends up being the same framework as before. After you discretize using an implicit method of your choice, but we are using the one-step Dirk methods that can be chosen to be L-stable, and typically we do third-order accuracy. At this point, we just have a fully discrete residual that we can plug into the framework before, just to algebra at this point. One little thing about the mesh velocities, we do formulate that equation by itself, just to get what we call stage-consistent velocities that are consistent with the way we discretize the actual PD. Here's our minimization framework. Again, it's exactly the same as before, just redefining what the little residual is and the error indicator residual. And there are a few differences, namely that we don't actually add the penalization of the mesh. Turns out we don't need to for these simple examples that we do, because basically we have a good initial guess. In general, you might need to. Of course, in general, you need topology changes if shocks bounce a lot or they merge, but in our examples here, we get away with not doing that. And we don't need other sophisticated line sorts. Again, we have very good initial guesses, that's why. And these initial guesses are good not just for the solution, but for the mesh as well. So for the mesh, using Rakhine-Huguenot-based estimator, we can actually move the interface itself. And in general, that will mess up the mesh a lot and invert it, so we do some smoothing. And that's our initial guess for the new mesh position. And for the solution, we can, for example, use the one from the previous time step. Here is 1D burgers using method of lines. You can see the typical characteristics of extremely sharp features without excessive number of elements. You cannot see the mesh here, but it's basically just moving the interfaces between these elements along with the problem, without knowing, of course, beforehand where it is. Here are space-time solutions that I'm going to skip for now and go straight to the Shu-Osher problem, where we can see the typical case where we resolve these. This is difficult because there's a shock, but there's also high frequency waves. So too much dissipation will make you bad at the lose amplitude at these oscillations, but we nail it well with very few elements actually, compared to a reference solution. And we have a 2D cases. We have 2D burger here that deforms this initially straight interface, and a blast wave that is just expanding like that with very good results. So there are a lot of future work here, in particular shock formation and solution transfer, but I will maybe leave that to the discussion section, and I'll be happy to discuss this much more then. Thank you very much.
Okay, so now we move to the last speaker of this session, Leonard Kamensky, and he'll be talking on bounds on the smallest eigenvalue of finite element equations with adaptive and isotropic meshes without regularity assumptions.
Welcome everyone. Here is Leonard Kamensky, and now we're talking about conditioning of finite elements on anisotropic meshes. Let's start this way. Consider a boundary value problem and the corresponding linear finite element system. Highly adapted meshes can have a strong influence on the system, and this can have a big impact on convergence and accuracy of the solution. For the conditioning, we estimate the extreme eigenvalues of A. The estimation of the largest eigenvalue is well understood. It's bounded by the largest eigenvalues of the local stiffness matrices. But a good bound for the smallest eigenvalue is quite difficult. So far, Most of the works require some mesh regularity in order to bound the constants in the estimate. So, what I want to show you here is that there is actually no need for such regularity assumptions. The first good bound was given by Bank and Scott, involving some average of the local mesh sizes. But they proved this bound only for isotropic adaptation. A more general result was given by Graham and MacLean. Their bound involves some average of the patch volumes and is valid for anisotropic meshes as well. In their estimate, the constant depends on the ratio H of the neighboring element volumes, here K and K prime. With some local regularity, H stays bounded, but if we have highly anisotropic meshes, such as Shishkin or Bakalov type, it can be very large. With Weizhang Huang and Hongo Shu, we derived a bound in terms of the element volumes without any conditions on the mesh regularity. Please note that here the constant does not depend on the mesh regularity. However, this element-wise averaging is not optimal either. Here, if we continue to squeeze this gray layer towards zero, the volume of the smallest element goes to zero as well, but the volume of the smallest patch still remains bounded. Can we obtain a better patch-wise estimate without mesh regularity assumptions? Let's take a look at the usual proof. It starts with an estimation of the H1 semi-norm through the best possible L norm, and it shouldn't end with the discrete L2 norm. In between, we sum up element-wise, then separate the nodal function values from the geometry contribution with the Holder's inequality, and then we switch to the discrete L2 norm using norm equivalence. The problem is that, at the end, the element-wise contributions do not fit well together to sum up into patch volumes. As a result, some compromise has to be done. Either some local regularity assumptions, or the bound has to be in terms of the mesh elements. So, how do we avoid this dead end? Well, we take the same idea as before, but this time, first, we switch to this discrete norm, and only then we apply Holder's inequality to extract the solution vector. This way, at the end, everything magically fits together, and this time there are no regularity-dependent constants. In 2D, the bound is similar, only that the mesh non-regularity is inside a logarithmic factor. So here you can see our first numerical example. The picture on the right is a zoom in around this area. The blue line shows the exact value, the orange the new bound, and the green and magenta the previous bounds. Here, as you can see, the new bound is closer to the exact value. This example illustrates an extreme case of a single layer refinement. We just squeeze these layers which go through the middle in the cube. This is artificial, but it shows well the differences in the bounds. Here, the exact value in blue stays constant, and the new bound in orange precisely follows the exact value. The bound by Graham and MacLean is far away, which is not surprising, since the constant in their estimate depends on the layer thickness. The bound in terms of mesh elements is better, because it doesn't have regularity-dependent constants, but, as we've seen before, its element-wise averaging is not optimal. Thank you very much for your attention, and greetings from Berlin.
Okay, so we've finished the video presentations. I encourage you to ask questions of the speakers, so please put them in the chat. We also now have Wei-Sang Wang who's joined us. He was a speaker in the first session, so you can also ask questions for Wei-Sang as well. I see some of the questions have started coming in. Let's see the first one. So this is a question for Lorenzo. It's from Pedro Diaz. It says, nice talk and nice applications. I didn't understand, how do you decide the mesh size and the refinement? Is there a target error, and is there a number of elements to reach? So Lorenzo, do you want to turn on your camera?
Can you see me?
Yes.
Hi everyone. Thanks for the question. And we specifically decided for the refined cell size for a ratio between the fine cell size to the internal length parameter, which is a characteristic length parameter for the phase field method, equal to 1/8. We decided to refine until we reach this specified ratio because this ratio allows to obtain more accurate solutions. And especially in a recent paper from Professor Pandolfi, the errors is compared between different ratio between the cell size to the internal length parameter. And on average, this ratio allows to obtain more accurate solution and reducing the overall error of the simulations. And we do not set a predefined number of elements to reach. We started with a coarse mesh, which had a ratio about the coarse cell size equal 2 times the internal length. And once we found the active elements, we start refining specifically into the active elements and into their surrounding elements in order to create a transition zone which allows for a more smooth transition from the refined elements to the coarse element. But we didn't have a target number of elements, so we just want to be sure about the final ratio between the cell size to the internal length parameter for the phase field in order to obtain accurate solutions.
All right, great, thank you. So now we have a question from Martin Bergman to Paroloff. What do you think of cutting the elements as shocks instead of manipulating?
Yes, I have. That's a great question. We've tried a lot of things. The main reason that doesn't work is that we actually do not. It's so super sensitive. We don't have a good estimate for where the shock is until we reach it, right? So we could have some sort of linear guess, but if we then were to cut the mesh and solve, first of all, we can't solve because if you miss the shock a little bit, it blows up. So basically, what we found is that we need something to smoothly manipulate both the mesh and the solution U. So we start off with some smooth solution U, maybe from a stabilized solver, and we move the mesh smoothly in whatever optimizer way you want to do. Now, if we wanted to suddenly just say, I know where the shock is, let's just refine there, it would be perfect, but we don't know where it is. And what I would say, if I wanted to use cut cells for this, I would actually do something like this, that I would predict that I need to cut, let's say, an edge somewhere, and I would throw in the location of where I cut it as a parameter, but I would constrain it. For example, the length along the edge in 2D, right? And I will constrain, but I would still have to solve for it. So the optimizer could smoothly slide the cutting point along that edge, for example. So I think you can totally do cut cells on this. The only thing I don't think is possible after a lot of tries is to suddenly, in a one shot, just say, here's the shock. Let's refine, not even in an iterative way, because you will get the flip-flop effect that you guess where the shock is, you try to solve, you stabilize, and then the shock moves a little bit and everything changes. So that's our little experience of that. I think it was essential to have, in fact, it was essential to have what we call a full space solution, full space solver that moves both the mesh and the solution. The solution is wrong all along until the shock is aligned, and then we nail the solution. And the way to understand why that is that if you're a little bit off, we can't solve because it blows up. There's no stabilization, which is the beauty of the method. That's why it's so accurate. But it's a great question. It's just so easy to have intuition about this. After playing around with it, it's just nothing works, right? And finally, we found a framework that kind of worked pretty well. So optimize for the cut, Martin. That's exactly what I meant by saying that there is a cut, but then you figure out where it is using the optimizer. I think that would work. And maybe I see there's another question for me, avoiding the mesh singularity. That's great. And we do have in our steady framework, by the way, let me apologize. I said in my talk, I realized now that this was the follow-up talk to my colleague, Matt Czar. And I don't know why I assumed that my talk was after his, but he's actually tomorrow in our third session. He's the last talk. So I screwed up the order a little bit because my point was to follow up on his talk and talk about the unsteady extension. But you'll see much more when he talks more because he's done all of this. He will give many more details about it. In his steady framework, in all our steady examples, we have a mesh regularization, which is a standard type of mesh deformation term that simply blows up. It's an optimizer. It will not let you optimize. Same thing that we've been using for our curved mesh deformations, basically, and curved mesh generations. So we have that term there. As I did mention quickly here in my fast talk, was that for these moving examples, we actually don't need that term. And that's just because they are too simple. Not too simple, but they are simple enough that our mesh moves such a little distance, so it just doesn't invert. In general, of course, if you let the shocks run around and do things, this error indicator is not going to stop you from, for example, collapsing elements. And we know that we don't want that for other reasons. So therefore, we add. In fact, if you, the thing we minimize is that residual square thing, the enriched residual, plus a penalty times the mesh regularization. So that's why we never get inverted elements.
All right, so thanks per. Let's go to some questions for other speakers, and we'll come back to you if there are more things later. Okay. All right. So looks like a question for Lorenzo from Juanjo Rodenas. So Lorenzo, would it be possible to unrefine the mesh once the crack tip is sufficiently far away, probably in combination with some kind of element erosion, in order to further reduce the computational cost?
We actually already did that in the presentation as well, but probably it's from the dimension of the mazes, it's not easily visible. We actually have a fully refined area around the advancing crack tip, so we can better capture the crack advancement, the crack propagation, bifurcation advancement in our model, while in the areas where the cracks has already nucleated and the crack pattern has been already established in the previous time step, we only refined where damage exceed a set damage threshold, alpha S. And by doing that, we can have a highly refined area only in the fully broken area, in the fully broken zone, while we also have a lesser refined area around that. While in the advancing crack area, in the advancing crack tip elements, we fully refine all the elements. Moreover, we also perform a parametric sensitivity analysis for the dimension, both of the adjacent elements to be refined, as well as for the dimension of the advanced of the active elements where the crack tip is modeled. And while for the global refinement strategies, these parameters does not affect too much the solutions. For the global local strategy, especially in the local solution, as we have a wider refined area, we obtain more accurate solution, but obviously it comes with a higher computational cost. But yeah, we implicitly kept the areas where damage has already been, where the domain has been already broken, refined only in the areas where it's fully broken, while for the advancing crack tip, we model all the area around the crack tip that advance.
Okay, here's another question, Lorenzo, also from Juanjo. Rodanus, appropriate modeling of cracks usually requires highly graded meshes around the close vicinity of the crack tip. Otherwise, you end up with pollution errors. Is a phase field approach avoiding the need of this kind of refinement?
Yeah, as already said, we kept the highly graded refinement around the crack tip, in fact, to avoid errors which can occur into the determination of the crack propagation and the crack path, which forms the different subsequent steps. And yeah, we kept the highly refined in a wider zone around the crack tip, while where the domain is fully broken, we just refine only on a smaller section where the damage exceed a set threshold to keep the degree of freedom as low as possible, but always obtaining accurate solutions. Yeah.
All right. I'm not sure if this question was answered. Per, did you catch the question about avoiding mesh singularity in the mesh optimization from Weizong?
Yeah, no, I don't think we covered it in the last.
Okay, I don't think you did. Yeah, do you want to go ahead and answer that? So it just says, nice talk, how to avoid mesh singularity in the mesh optimization.
Oh, sorry, that one. I thought you meant the other one. That one I did cover, exactly. I jumped ahead, yeah.
Yeah, he answered the question. Yeah.
Okay, I'm sorry. All
Thank
right,
you.
but now we're going to ask Weizong a question. This came from the first session, and I've already forgotten who asked it, but it was thanks for this interesting talk. How is the regularization effective compared to existing approaches? And do they have Newton with linear search or alternative direction minimization? So Weizong?
Well, it is, yeah. This is very interesting question. To answer the question, because very simple, I don't know. Okay, so but first of all, the regularization method is very effective. Actually, you do not need to do anything. The Newton iteration just converges nicely. And we also tried, the reasons I say I don't know for other methods, we try a number of variants of Newton methods. And we just could not get the convergence because the problem is inherently singular. The Jacobi does not exist at those points. So we try several Newton's methods, and we get the residual down to 10 to the minus 7, and then we just cannot get it down anymore. So that's why, okay, we say we do not know. We read as a couple of papers, we try to replace, but most of the papers, they just stop, present more results, like around 10, the error is around, residual is around 10 to minus 7. So we want to get them down, to make sure the method is convergent, but we did not get that. We failed to do that. That's the reason. But for the method itself, the regularization is very effective. So we can, we don't do anything, just use the very standard Newton iteration, and we can easily get to 10 to the Randolph error level. Thank you.
Okay, thank you. Oh yes, that question was by Modesar Shekar. Now I'm remembering. Thank you, Modesar, for putting thank you in the chat so we could remember that question was from you. All right, I'm gonna ask a question for Leonard Kaminsky. I don't have it typed, so I'll just speak my question. But so you were doing these bounds on the smallest eigenvalues tied to finite element equations. So I'm wondering, what advice would you give people in terms of designing sort of adaptive anisotropic meshes? I mean, you had some nice examples tied to your theory, but can you sort of extract the sort of nuggets out of the theory to give people advice on how to maybe design these kind of meshes for their simulation?
Hello, can you hear me well? It all works?
Yes,
okay.
please.
Thank you. Very nice to see all you people, and just missing conferences in life. Yes. So for designing meshes for the finite element solutions, directly, it's probably a bit more complicated. I'm not a really finite element solution guy. Directly, the one thing that I kind of get out from all this is that if you have a local refinement, that means that you don't do your isotropic mesh all over the mesh. So if you have some particular features that stays local, then it is not so bad, because at the end, what counts is some sort of an average. So what I didn't show in this talk at the beginning was, so if you take just as it is the stiffness matrix for this simple problem, then the largest eigenvalue will depend on the local feature. So one badly shaped element will explode your largest eigenvalue. However, this is treated really well with preconditioning, and so there you can rescale back with diagonal scaling or something similar. The largest eigenvalue is just to be bounded by some constant, and so all this ugly stuff will move into the smallest eigenvalue, some sort of an average. So at the end, there will be still some sort of a volume weight shape quality average, something like this. And so the two things I learned from this was, the first, in the higher dimensions, it's kind of the shape of the larger element is more important. And the second one is, I said, if you have a local refinement or locally something very anisotropic or a bit of ugly, it is not as bad. So it will not dramatically, it should not dramatically make everything worse, at least from this theoretical point of view. But I think the real life with some more complicated problem than just the fusion problem I showed you probably is much more complicated. But the point is that I think it took about, say, altogether from the first papers, like 50 years to get to the end, to remove all this mesh regularity. And people tried it, basically every decade, someone else tried to move it forward and someone else moved it further, until now I think we got, at least for this example, it somehow without these constants. I hope this answers somehow.
Yes,
question.
no, this is good. Yeah, I was just looking for the sort of, the big picture summary, what the takeaways are. So because there's a lot of interest, I think, these days in, well, it's working at the intersection of sort of meshing and finite elements, right? So yeah.
Well, I'm still learning, so I think I will continue to see if I can get more insights. Or still, sometimes I got some insights, sometimes it's still blurry. I don't think I still really understood it until the end. But I think, yes, I think kind of the major takeoff is if it's a local refinement, it should not be so bad. So basically, if your whole mesh is ugly, then there is no hope. But if it's something local, it's not as bad. So just saying one bad element, if you have a good preconditioner, so just one bad element should not spoil it, put it this way.
Do you have comments on what it would take to get a good preconditioner?
Ooh, this is also a good question, because to get something theoretically done was provable was difficult enough. So far, we considered only just the standard Jacobi kind of diagonal preconditioning, because this one is, at least this one is very easily to squeeze through all the estimates and all the analysis we do. But as I said, if you just use something diagonal preconditioning, or actually to put it other way around, if you use any sort of preconditioning which is which is invariant towards diagonal scaling, some sort of a Koleski or something, incomplete Koleski, then it looks like your diagonal scaling is already inside implicitly. So basically, from that perspective, if you use this sort of preconditioners, you can assume that you already applied sort of a diagonal preconditioning. That means you already moved away from the kind of the worst element spoilers to just some average aspect ratio. So I think there was a very short note in our paper with Weizhang and Hongo 2014 at the end. So if you just look at the incomplete Koleski decomposition, then you just see it's already inside Masony.
Okay, great. All right, so now let's go to a question to Capuchin. Would it be possible or useful to use MMG for adaptive refinement everywhere in the problem? And this question is from Jerome Wackers.
Hello everyone. Thank you for this interesting question. The MMG adaptive refinement is used before the insertion of the contact line, because in the GeoModel, the mesh resolution is defined according to the simulator's heuristics and rock properties, and in particular here, according to shear wave velocities. So we have to control the element size in each materials for the simulation, and so we want that the mesh resolution is unchanged during the mesh modification. So yeah, the MMG adaptive refinement is used only in the modified regions.
Okay. Wonderful.
You're welcome.
All right, so some more questions for these speakers. This has been some great discussion. Do we have more questions? I guess I'll ask a follow-up question for Wei Song. Maybe you slightly touched on this, but maybe not quite exactly. So Wei Song, I know when you tried the different kinds of Newton methods with the brittle fracture and so on, were you looking at sort of line searches? Did you ever need trust regions? Does that change anything or not really based on the singularity issues you're facing?
Can you say again? Sorry. Yeah.
Sure. Let me repeat the question. I don't know if I can word it exactly the same because it's just coming off the top of my mind. But when you were trying these different Newton methods with your brittle fracture simulations, were you looking at? I mean, did it matter if you use line search versus trust regions, or was that not important since the singularity was sort of the main issue?
We did not specifically look at the change the region and something like that. We use the MATLAB optimization, and we try different methods. We also try to use like a damped Newton and something like that. So the major thing is that the Jacobian matrix at the crack point, because we cannot compute it very accurate, we use a finite difference approximation. So we just don't know if that is caused the trouble or some others. So all the methods we try, they can get very good results until like a 10 to the -7. But we find out at that time the solution still change a little bit. So we want to get down to 10 - 10 or 10 minus like a 13 or something like that. We just cannot get to that point. So I think this may be called it is caused by the approximation to the Jacobian finite difference approximation to a Jacobian. That is the accuracy, right? If we use the finite difference, that accuracy 10 to the -7. Yeah.
Okay. Right. Thank you.
Okay.
So I have another question I want to ask Capucine. So the question is about the seismic wave simulations. So what are some of the main challenges that you're facing going forward with your mesh refinement in that context? Of course, we watched your video, but they're also short presentations. So maybe you could say a few more details on some of the challenges you're facing going forward.
Okay. Yes. Yes. There's a lot of challenges for the wave propagation simulations, because okay, maybe I can share my screen.
Yeah, give it a try, and if we need to ask the host to help us, we will, or maybe you can share.
All right.
Yeah, you should be able to share. Yeah. Perfect.
Okay, thank you. Okay.
Do you see my screen? Yes.
Yes.
Okay. So yes. In my work, we want to know if we could use the method that I presented to you in an inverse loop. So we want to run wave propagation simulation on all the mesh models, and we have some difficulties with the mesh quality, and in particular near the boundaries, the existing boundaries, because in geomodels we have very often low angles and very thin layers, so the mesh quality are quite bad in such an area. And for that, we propose to locally change the implicit definition of the line to avoid the creation of very thin triangle near the existing boundaries, because the mesh quality is have a very high impact on the simulation times that we can see here, and the time of computation is can increase of 1,000 times if we let these very thin triangles. So the main challenges of my work is to maintain the conformity all along the boundaries and the inserted lines, and to keep mesh quality quite good for the to keep a simulation time reasonable.
And what is reasonable here in this particular application context?
With my computer, that have just 4 cores, a reasonable time is 6 hours maximum.
Okay. And that's for how large a mesh is? You might have said, I might have missed that detail.
This mesh have 20,000 triangles.
Okay.
So it's not a very large models, but the worst simulation have take 25 days. So
Okay.
it's too long for this model. Too long.
It's the PDE simulation that takes a long time, I guess. Yeah. So, okay. Okay, great. So I also want to. Oh, go ahead.
So then can I ask a question to Lawrence?
Yes. Okay.
Okay, so for the I believe this is for the simulation of a brittle fracture, and so I just wonder, do you observe or did you observe any like a force cracking with the current model?
A force cracking in the can you elaborate a bit more?
Okay,
Because
all right.
sorry.
Yeah, I give you a little bit specific. So for now, for when you use any like this is called tensor decomposition or energy decomposition schemes. So basically what they do is that near the crack, or maybe on the crack, they degrade the energy, the active energy.
Okay.
But still the positive energy is not taken away. This will give, usually this will give some force, even the material is totally become, a gap there. There's no material there, it's cracked there.
Okay.
Yeah, this is like, for example, for shear test, the standard benchmark test, the shear test, the crack is not going down. Instead, it can go up, and also the crack can be going around the boundary. And this is called, force cracking. Did you see anything like that?
For the test we run, we just run a surfing condition test and the abrupt crack propagation test was shown, but for those specific tests we did not have this kind of problem. And for example, forces are not present once the material is fully broken and the complete crack pattern is formed. We did not have residual forces nor particular or strange behavior of the material. Other than that, I mean, for example, for shear cracks, together with Professor Freddi and Professor Alessi, we observed that the phase field model cannot reproduce correct shear crack with the standard formulation, but mixed formulation or selective reduced integration should be used in order to obtain the accurate solutions in terms of energies and forces. But for this particular case with mesh refinement, we did not had those kind of problems, those residual forces or particular unexpected crack patterns.
Okay, thank you. Yeah,
I don't know. I don't know if I answered the.
No, you mentioned that. I
question.
think, yeah, thank you. Yeah, you mentioned that something like with a shared test. You know, before it seems like there's some issues there. So it's not the calculation, it's the modeling. It's part of the problems, the modeling. Yeah.
Yeah.
Yeah. Thank you.
You're welcome.
All right, so I wanted to ask per a question.
All right.
So per when you're doing your PDE constraint optimization, you know, framework and dealing with meshes and these shocks, do you have any problems or challenges with convergence or conditioning or anything like that when you're solving the PDE?
Yeah. Well, so to begin with, we're not directly solving the PD. It's a PD constraint.
No, I understand. Yeah, yeah.
So if we were to do what's called the elimination method, which means that you basically only solve for the mesh, and every time you give me a mesh, I could solve the PD, right? Then it would be equivalent to whatever PD you're solving. So it would be, I mean, it wouldn't be different from what I do, right? We can't do that. Remember the full space thing I said? You got to solve for them simultaneously. For the simple reason that if the mesh isn't aligned, we can't solve.
Right.
And so we do this. These solvers are basically simultaneously finding steepest descent gradients in solution and mesh space, right? And then moving according to whatever Broyd and quasi-Newton schemes in those directions, right? Now, at the end of the day, there is, of course, a solver, and it's written such that we use exactly our PD solvers. And it ends up being the same type of system that we have. So unless you mess up the mesh and make it, inverted element or something, those systems, those solvers carry on, behave exactly like they would if you were to solve the PD problem itself on a given mesh. So I would say basically no. Basically, it's fine as long as you don't mess up the mesh, which of course I can't guarantee. Or that you try to solve too much on them. I mean, there are a number. It's kind of a little bit of magic and very sensitive, right? But the line searchers itself easily shoot you into a non-viable region, right? And then it's important to quickly evaluate the residual. And sometimes the residual is fine, but the Jacobian is horrible. So you got to, you got to have a lot of these backtracks where you just fail and backtrack, right? And that's why you have line searches. It's not a stiffness issue, but the solvers are complex in that sense. Although that's standard for super nonlinear PD constrained optimization.
Right.
So it's not fun.
Right. How computationally expensive is your method too? It could be runtime or it could be flop. I mean, I don't care how you sort of give the answer.
So the key thing is the number of iterations, right? Because we solve the PD basically each time. If we just look at the steady state, because I talked about the extension to unsteady, but just a steady, right? I mean, it's basically the number of times. So if you have a good initial guess, I think it's pretty good news. Because if you do a steady case and you have a good initial guess, maybe from a finite volume scheme or from some other scheme, right? Then it's 1 and 2 minus. It's not 10 iterations, but neither is 100, right? It's typically maybe 50, right? So it's going
Okay.
to cost 50 solves. Remember, the competition here is standard adapted mesh refinement, right? Which
Yeah.
also solves over many times.
Sure.
And the payoff here is fantastic because we don't add all those elements. We just align, right? So to me, if we solve less than 100 times from scratch or from a good initial guess to an aligned mesh, that's fine, right? But the even better news is that for the time dependent case, for the unsteady case, we can solve in just a few iterations because we have such good initial guesses. The mesh is just moving a little bit each time, right? So I don't know. It's a constant factor more expensive than solving that it would be to solve with shock capturing and stuff. And I believe it will pay off if you work out all the details. It should pay off because you have so many fewer elements. But for a time dependent problem, I would say that factor is between 1 and 10. For the first one, for the steady case, I would say maybe between 10 and 100.
Okay, great. All right, so any last minute questions? We have 2 more minutes, and at the very end, I'll close and give an announcement about tomorrow. Any questions for any of our speakers that anyone wants to ask at the last minute here? Okay, so I'm not seeing any or hearing any. But this has been a very good discussion, and we've had some interesting talks today in these 2 sessions. So let me just say briefly that we'll have part 3 tomorrow for this session, which will be at 14:30. And in general, I'll just share the screen quickly so you can see the program for the entire conference for tomorrow. So the conference itself starts at 9. And then our session will be, as you can see down here, at 14:30 near the end, and that will be our final session. So thanks for joining us today, and we hope to see you back tomorrow for part 3. Have a good day.